Okay, folks, I've had a few of you ask about, this is my MATLAB number 6. It's from section 14.4, corresponds to number 40 in the textbook. So here we're given a parameterization of some curve, and we're asked to do two things. First of all, to determine whether or not the curve uses the arc length as a parameter. And if it doesn't, it wants us to go ahead and reparameterize this curve so it does have the arc length as a parameter. So remember what that means. When we say that it has the arc length as a parameter, we mean that the length of the curve will equal the length of the, and I'll just put this in quotes here, the time interval. That is the value t, or sometimes or later on we'll use s, but that's the real valued component of this parameterized curve. And so we won't actually check all the way through to make sure that the length of the curve is equal to the length of the time interval, or I'll compute it for you, but we won't do that calculation. But remember that we say that one way to check to see if it has the arc length parameter is if the speed vector is equal to 1. So if the norm of the velocity vector or the speed vector is equal to 1 for your parameterized curve, r of t, then it has the arc length parameterization. Okay. So for our function here, for our vector valued function here, we've got r of t is equal to 5t squared, comma 6t squared, comma 2 square root of 15 t squared, for a particular choice of time values for 1 less than or equal to t less than or equal to 4. So the first thing we should do is we should go ahead and compute the speed vector. So to do that, first of all, we're going to differentiate the position vector. That will give us our velocity vector. And if we do that, we end up with 10t plus, or excuse me, 10t for the first coordinate, 12t for the second coordinate, and 4 square root of 15 t for the third coordinate. And then if we go ahead and compute our speed vector, remember that's just the norm, that's just the norm of the velocity vector. So we take the square root of 10t squared that squared should be on the outside there, plus 12t squared plus 4 square root of 15 t quantity squared. And let's see here, if we compute that, that gives us the square root of 484 t squared. 484 is a perfect square, so we get 22, and then the square root of t squared is the absolute value of t. But because we know that our time values are only positive time values, we can just go ahead and write that as 22t. So what we could say is that if you think about this projection, remember we've got some curve in 3 space here, and it's being parameterized by time. So we've got these time vectors, moving it out in time. Well, the speed of this changes with time. In fact, it changes linearly with time, and it continues to speed up. But more specifically, what is the speed vector not? The speed of this parameterized curve is not 1, so that it doesn't have the arc length parameterization. So that's the good enough check, and that's all you need to do for this. I just want to reiterate what we mean, though, by that arc length parameterization. So if I were to go ahead and integrate this, calculate this arc length by integrating the speed function, we'd have the integral from 1 to 4 of 22t dt, and if you were to compute that, you would get 165. And more specifically, what is that not? That's not 4 minus 1, which is 3. That's our time interval. So our arc length is not the same. Our arc length is not the same as our time interval, which is why we say that this is not parameterized with the arc length parameter. Okay? So what do we need to do? Well, we need to modify this. So we have a theorem in the book, and I'll point this out, but it's really just a matter of taking the derivative of our speed function. And so we could say that ds is equal to the magnitude of our velocity function, or that is our speed function, times dt. So in our case, we end up with ds is equal to 22t dt. So now we'll go ahead and integrate both sides. So integrating both sides gives us the integral of ds is equal to the integral of 22t dt, which gives us that s is equal to 11t squared. And here's the issue right here, plus c, plus an arbitrary constant. Now, normally it doesn't matter what you pick. It doesn't matter what you choose for c. So if it doesn't matter your choice for c, I would argue that maybe the best choice for c is 0, because that just keeps the entire expression smaller. Okay? But it turns out MyMathLab wants us to pick a particular value for c, and I'll point that out when we get to talking about what the new time interval is. Okay? So let's go ahead and normally what we do is, if we want to go ahead and do this integral substitution that we're aiming to do with this new parameterization, is that we'd want to solve for t. So if we go ahead and start that process in solving for t, we'd have s minus c is equal to 11t squared, or that s minus c all over 11 is equal to t squared. And normally what I would then do in a typical problem is I would go ahead and finish solving for t so I could make that substitution. So I would take plus or minus the square root of both sides and continue. But if we look at our original parameterization, we've got these t squared components, so there's no reason to take the square root of both sides. We're just going to go ahead and in place of the t squareds in our original parameterization, we're now going to give this the parameterization of this curve in terms of s and not t, and so we'll replace all of the t squareds with s minus c over 11. So this gives us 5 times s minus c over 11 for the first coordinate. And what were our other two? We have 6 times s minus c over 11. And what's our last one? It is 2 square root of 15 times s minus c all over 11. Okay. And that's our new parameterization, but of course a parameterization needs to have a domain with it, and we need to choose our values of s. Okay? So originally t was 1. So when t was 1, for our left limit there for our parameterization, we would have that s is equal to 11t squared plus c, so we'd have that s is equal to 11 times 1 squared plus c, or s is equal to 11 plus c. Okay? And when t is 4, we would have that s is equal to 11 times 4 squared plus c, or 11 times 16 plus c, which comes out to be, let me check that, 176 plus c. So here you can see that, if you chose c to be 0, this would have made the whole problem look a lot easier. So let me give a correct answer. This is not the one MyMathLab's looking for, but this is a correct answer, that we'd have 5 times s over 11, comma 6 times s over 11, comma 2 square root of 15 times s over 11. And that's if we chose 0 for c, so that would be for 11 less than or equal to s, less than or equal to 176. And I would argue that's a very good way to have reparameterized this so that this has the arc length parameterization. And everything's fine with this. But what MyMathLab wants you to do is they want you to now, at this point, pick c so that the left limit is 0. And that's what you need to do to make this work. So we need to choose a value for c to make this left limit 0. So we're going to pick c is equal to minus 11. So then once we do that, we will have a different parameterization. We will have that r of s is equal to 5 times s minus, minus a minus 11, so that makes it plus 11 over 11, comma 6 times s plus 11 over 11, comma, 2 square root of 15 times s plus 11 all over 11. And then what do we get for our range, for our s values? Well, they're going to go from 0 less than or equal to s, which is now less than or equal to, so we take 176 and we subtract 11, and we have 165 for that range. Notice that this is the same. First of all, what is the length of this time interval? The length of this time interval is 165. That's precisely what we got way back up here when we evaluated the arc length under the original parameterization. Okay, and so we have 165. So that's correct. But so was this answer up here. Notice this also has a time interval of 165, and if you were to, in either case, take the integral, let's go ahead and do it for the parameterization MyMathLab wants, the integral from 0 to 165 of absolute value of r prime of t, or excuse me, not dt, because we're in s land now, of s ds, you would get 165 for that value. But that's also what you would get over here if you did the comparable integration. Okay? So this is a really good problem because we get a chance to practice this reparameterization of a curve so that it has the arc length parameterization. That means that the length of the interval of time is equal to the arc length, and that's what we call the most natural choice for parameterization. That's like when we parameterize a circle, we choose to use x equals the cosine of t and y equals the sine of t for t between 0 and 2 pi. That's the most natural choice of parameterization. We could use other parameterizations, but this one has an arc length that's equivalent to 2 pi, which is equivalent to our time signature. So this procedure of reparameterizing one of our curves is a very useful tool, and we'll use it quite a bit. But what I found especially frustrating about this is when we go to come up with an expression for s in terms of time, there is an arbitrary constant there, and I think the most natural choice is 0. But as far as coming up with a correct answer, it doesn't matter which choice you pick. However, MyMathLab was programmed that it wants you to pick a choice of constant so that that left limit is 0 here. So folks, that's a pretty lengthy video. I hope that clarifies any questions. If it doesn't, please let me know, and I'd be happy to go through it more. Thank you.